what is the force acting on the wire? So how do you visualize this? In exam, they'll give you this question and you have to come up with the picture yourself, right? So they said that the magnetic field and the wire happen to be 30-degree angle. So that would mean that this wire is like this. And the angle here is not what anymore? 90. Will there be force if it's not 90? Yes. The only time there won't be any force if it's how much? 0, parallel. Okay, that's always there's a force. And the force keeps decreasing. Last year, question asked, some students couldn't answer it. I was surprised why. Question chilo, a person rotates a wire and goes from perpendicular to parallel. And they asked you to draw a graph for the force versus angle. What's the graph? Yeah, it's a sine graph. It's just going to be a quarter of a sine graph because you go from 90 to 0, right? So it's just going to be that, okay? Not the full sine graph out there. That was it. That's it. So just keep in mind. But then there was a follow-up question that how can you make it a straight line? Like what relationship between force and angle will give you a straight line? And if I plot a graph for force versus something of an angle, what would that have to be to give me a straight line? Like what quantity of force is directly proportional to a function of an angle? That's maybe my question wasn't clear. Question that's paper 5 actually, by the way, not paper 4. So the question was actually asking you to find the relationship between force and sine theta. And force and sine theta happen to be directly proportional. It's not going to be like that. Because once you take the sine function, right, it's not following that thing. The angle is what's changing there. So yeah, anyways, the point I'm trying to make here is that the maximum is going to be how much? 90, and the minimum is going to be 0. But this question says that the angle between both of them is 30 degrees. So this angle is 30 degree here, that one, right? Can you tell me what can I do here? Do I break my magnetic field into components, or do I break my current into components, or is both fine? So technically speaking, like in terms of math, both is fine because you just take one as your reference and the other as that, right? But in terms of physics, you can't break the current because current is not a vector. It's passing through the wire. There's nothing of it that goes this way, that way. It's only in the wire. But the magnetic field has like parts that are here and there. Okay, so magnetic field is what, a vector. So the picture could turn into a problem, and the only purpose of this question is so that you can understand how to picture this better. So how can I break my magnetic field into components? Let's try to go outside the comfort zone, because the exam they'll just make you break the magnetic field, and usually students don't know what to do. So can you tell me if this is B? This is your magnetic flux, right? And the angle here is theta or 30. How can I break it into components? 90 minus 30 would give me that angle, right? Would you want to use that angle? You can actually use this angle. Can you tell me the... Okay, I'll make a question. Huh? That's also 30, yes. Okay, give me the expression for the magnetic flux density that's perpendicular to the current. Yes, very good. Okay, let me show you how it works. So you need to break it down into two components, taking this as the center. Edike ekta component jabe, arta component edike jabe, which is like that. Do you see what's happening here? So this is the one with the angle. This is the one opposite to the angle. And this one is what to your current, perpendicular, right? Eventually, you'll find that it turns out to be a what function? Sine theta function, which is why the formula is there. But don't rely on this sine theta all the time. As I told you, examine, they might give you which angle rather, that one. Talking about cosine, however. So you have to, see it for yourself and then apply them. Anyways, আশা করি তোমরা বুঝছো যে অ্যাঙ্গেলটা কোনটা হবে. This is going to be B cos theta. B cos theta is going to have no impact on your outcome because it's parallel to the current. And this one is going to be B sine theta. And this B sine theta of this magnetic field is what to the current? Perpendicular. And now that if I want to find the force, or also কি করতে এখানে force বের করতে হবে. So your F is equal to B. B is 0.05, so 0.05 into sine 30 into what is the current going to be? 0.4 into length হচ্ছে মেনশন করা নেই মনে এখানে আচ্ছা লেন্থ বলার কথা দাঁড়া একটা সেকেন্ড চেক করি or 20 centimeter. So yeah, this is 20 centimeter. So effective length হচ্ছে 20 divided by 100 and এটা করলে যেটা আসে that's going to be the answer. কেটে চেক করতে কত আসে 0.002. Right, so that's the topic. This is what topic? This is the interaction of magnetic field and your current conductor. It's also known as a motor effect, right? So we have done this last class. So ask him to topic start. If you have any questions, you can let me know. So basically this, right? When they interact, they create a strong and a weak magnetic field. The strong and the weak causes a distortion that causes a force to be exerted, also known as the Lorentz force. And this is how you find it experimentally. And the thing that you need to be aware of is the angle role here. Okay. Right, so that's our motor effect from O-levels. এখন হচ্ছে we'll start something little different. এটার জন্য can you go to page 123? This wasn't there in your O-levels. I slightly rushed through the previous topic because it was entirely part of your O-levels with just a new equation. This one though, it's like a completely new topic. Okay. So this is charges in magnetic field. আর তোমাদের syllabus এখান থেকে অনেক কিছু জিজ্ঞেস করে and there are experiments also. So charges in So yes, how do charges interact in a magnetic field? So first of all, why would charges interact in a magnetic field? What's the reason behind this? So I'm actually জিনিসটা ভুল শিখি না, we learn in a wrong sequence. It is charges what only interacts with the magnetic field. Current is just after effect of it. So I'll explain what I mean by that. So it turns out charges, any charge plus minus, has like a magnetic field generated around it. Magnetic field has been found to be associated with the presence of charge. That's what we know. And I think I told you the electrons, one is the spin of the electron that produces it, right? So when your charge is in a magnetic field, let's say a uniform magnetic field like this, what happens is that the magnetic field of the charge interacts with the magnetic field of the what? The magnet, right? And as a result, force is exerted. But there was a catch. This, baffled physicists for some time. Why? Because they knew that there was a field called the electric field. And the electric field also applies a force on what? A charge. তাহলে এখানে ফোর্সটা কখন exert হবে? So it turns out the force of magnetic field will only be exerted on a charge if your charge is moving. That's the first and only requirement. Okay, so if your charge is moving, then only a magnetic field interacts with it. Otherwise, it doesn't interact. So if it's stationary, the field doesn't interact with the magnetic field. And that's the reason why the definition of magnetic field, there are two versions. One is it's a region in which a permanent magnet experiences force or a what charge experiences force, a moving charge. ওইখানে আরেকটা জিনিস স্পেসিফাই করতে হয়. I think recent paperগুলোতে I saw they wanted not only moving, a moving charge does what to the field? Perpendicular. So if your charge moves parallel to the field, তাহলে হবে না. So it has to be a moving charge that's perpendicular to the field. Then only what will the charge experience? A force. And that force is going to be what to the field and the movement? Perpendicular. So basically, when it comes to the vectors involved here, always remember they all need to be what to each other? Perpendicular. Okay, parallel কিছু হবে না. And right, so this is the magnetic field that I have. It's a uniform magnetic field. What would this charge do if it starts to move here? So it turns out as the charge starts to move here, it experiences a force. And this is the movement. Okay, so I'll label this here V. And the charge here is Q. That's it. And it's a positive charge. Which way will it move? So we can use an idea we have seen before. Fleming's left-hand rule. So let's revisit Fleming's left-hand rule. What was it? FBI. I was what? Current. B was what? Direction of magnetic field. And F was what? The direction of force, right? Now we'll dissect the current. Current definition, the rate of flow, positive charge. I mean, in our version, the conventional current is positive charge, right? Can't I imagine this one charge moving here is like a current? Because it's by definition what? A positive charge moving. So what we'll do here is we'll apply left-hand rule here as well. Nothing will be different here. Instead of current, the direction of my charge would be my direction of current here, right? So which way is my charge moving? To the right. Which way, the movement of the charge initially, which way is my magnetic flux here? Into the screen, which is a thumb pointed upwards, right? So what we notice here is that the charge here will start to deflect and go which way? Up. And then it moves up here like that, right? Now, we realize something happening, which is in an electric field, your charge would have gone like that. And then we have done this topic, it's the projectile motion or moton, it'll just deflect, right? Here it doesn't do that. Here it does something much more complex. So as the charged particle moves upwards, and let's say it's moving up like that, let's assume it's moving this way right now, like that. Can you tell me if it's moving this way, that's the direction of movement, right? Velocity. Which way is the force going to act? So ekhane force kintu act korche erokom, right? Ekhane force ta kothay act korbe if it's moving up like that. So yeah, FBI, current upwards, magnetic flux into the page, which way is the force? This way, right? And then you see that the particle now won't continue to go in that arc. It actually goes which way? Back. Edike chole jay. And I want to cut to the chase here. At any given point, this charged particle will experience a force that is what to the velocity, perpendicular, right? What is that the requirement for? Yeah, and eventually any charged particle in any magnetic field, right, will end up going in circles. Why? Because they have a perfect force always acting towards the center, and that force is called the centripetal force, right? So this chapter is the chapter where circular motion makes its actual entry. Motion in a circle, or just partial like demonstration. We saw it in gravitational field, but this is the topic where we have to see a lot of it. Okay, so before I start, I just want to do a quick recap of all the equations of circular motion because we need them. So what is omega? 2 pi by t, right? What is V? Omega R. What is centripetal force? mv square by R, or m omega square R. Clear? So these are the 4 equations for circular motion. Typically. So yeah, this these 4, right? Yeah, this one, that, and that. Okay, so let's get back here. So my charged particle is moving, and it will continue to move in a circle. I will show that later on in a diagram, but you get my point that there's always a force acting which way to the motion, perpendicular, right? Okay, now what is the formula for the force here? And I have to be honest here, tomato course all levels. If you remember, there was a small part of it in radioactivity where an alpha particle and a beta particle enter a magnetic field, and the alpha goes up like that, and the beta spirals. And I said there is like an A-level thing why it spirals. This is the reason why it spirals. You get my point? So will the alpha spiral as well? Yes, absolutely. But the problem is we never get to see that. Why? We'll do math and see the radius of an alpha particle spiraling is around 3 meters. So if you're doing like an experiment in a box of that size, right, the alpha basically does 0 deflection. It goes almost straight through. The beta can very easily observe to be spiral. But if the chamber was the size of this room, right, you'd see a proper circle made by the alpha. Okay. So anyways, it's a power paper. Equation the velocities also. Well, it depends on the source. Radioactive decay produces alpha, right? And the radioactive decay can give you a varying range of values. So it can vary. If it's a very fast-moving alpha, it'll produce a very large radius. If it's a slow-moving alpha, it'll like produce a small radius. Oh, so let's say you do an experiment and the alpha particle is very low energy, right? Yes, it'll produce a small one. Still, it wouldn't be like, enough to be seen in a box because alpha's mass is very high compared to electron. Now, let's say you do make the alpha go that small. What will the electron do? What will the electron do in that same field? It'll form like a dot. You have to understand alpha to kombe, electron to aru kombe. So তখন দেখা যাবে যে electron কিছুই দেখতে পারতেছে না, it doesn't do anything. I'll show you an animation, but the electron just forms a dot, but it's actually spiraling in that dot. Okay, so what's the formula here? So formula to derivation dite pare, I'll show you how to derive it. So we know, according to motor effect, what is the formula for the force? F equals to B I L sine theta, right? Okay. Now, what is a further breakdown here? So I is current, right? What's the formula for current? Rate of flow of charge, right? So current charge divided by time times L times sine theta. Now, if I take the Q out and take the length that it travels in the unit time, what is the amount of length covered per unit time? Velocity. So from there, you find that the force experienced by a charge in a magnetic field is BQV sine theta. And this was actually the original equation that was derived. Amra F equals to BIL পরে বের করছি. This was the first equation that we knew. So yeah, that's the formula. Again, the same laws apply here as the previous one. They all need to be what to each other for this to be viable. Perpendicular. What if it's not perpendicular? Again, components play a role. Okay. So তোমরা কি বুঝছো এটা? Any question থাকলে আমাকে বলতে পারো. Now, I'll show you some complex versions of this, okay? Because তোমাদের question যখন করে, they'll do this one, which is, it's difficult to show on a page, but I'll try. This is your magnetic field. And the magnetic field that I'm drawing right now is not flat. It's skewed. Think of a paper. The paper is like this. I'm drawing the magnetic field on the paper right now. তোমরা কি visualize করতে পারছো what I'm trying to do? So the paper is not flat anymore. Achha? So that's your magnetic field. And it's a uniform magnetic field, by the way. The reason why it looks a little distorted is because it's on the paper and the paper is not flat. Flat, but not from our point of view. So you have your magnetic field here. And a charged particle enters like this. What will the charged particle do in the magnetic field? So we just saw right now, it'll enter and go in a circle, spiral. Is that okay with everyone? Achha. Now, turns out, we always under assume what's happening because magnetic field is three-dimensional. There's height to it, there's width to it, there's breadth to it. So it's like a three-dimensional space. And let's say your charged particle doesn't enter straight like that. It enters at an angle into this field. So if it enters at an angle, this is the angle. So your particle now has two things it can do. It's supposed to go which way? Down. And it's supposed to go where as well simultaneously? Forwards, right? So I'll draw and show you the diagram to clarify. So yeah, this is the angle. The particle is entering the field at an angle. And this is the direction of the particle's movement, okay? You need to figure out what kind of path will the particle take in this field. So in room context example easier. This whole room is a uniform magnetic field. My charged particle here enters like that. So my magnetic field and my charged particle are what to each other? Perpendicular. So particle to enter kore erokom A plane circle kore thakbe. That's straightforward. But what if it enters at an angle? So যখন angle enter kore, what does the particle do? Like, does it spiral, or like, what do you think happens? Because this is not really part of our syllabus material, but it's a question paper question. And I feel it's a little unfair that they give this, but aage theke tomnake heads up দিয়ে রাখতে চাই. Yes, very good. Can you tell me what kind of shape would that be if it goes in a circle and descends? Yes, it forms a helix, like a spring. It is spring. Do you see how the path is of the spring? The particle will actually do that. So the particle will enter the field and it'll do this. It'll go in circles and it'll go which way at the same time? Downwards. Why is that so? I think tomorrow to figure out there's a component going to be this way, right? If this is V and that is my theta, this is going to be V sine theta. And there's going to be a component here. What is that? V cos theta. One of them is perpendicular to the field. Which one? V cos theta. The V cos theta would be responsible for making your particle undergo what motion? Circular motion. But there's a V sine theta though. Which way? Downwards. So the particle will try to go in a circle, but simultaneously go which way? down, right? And it basically does this. It goes down like that. Clear? So the downward movement is because of the vertical component, and the spiraling is due to the horizontal component. Because as it enters here, I think you can understand that there'll be a watt force acting on it, a centripetal force towards the center. So this is like most complicated I've seen in terms of diagram here. Yes. V cos theta. Oh, so the magnetic field that you see here, a magnetic field that draw grade 2. The magnetic field here is these lines here. And cross mane kondike into the page, right? So the magnetic field is like that. So the magnetic field and your particle here are perpendicular. But magnetic field and this component are what to each other? Parallel. So this component doesn't do any circular motion. Okay. Are you clear about this much? Achha, okay. So I'll show you one more thing, and then I will give you some notes on this. So the next thing hoche, what is the relationship between radius, magnetic flux density, tarpor hoche, mass, and everything? So how do you figure that out? So we need to look for circular motion here. So eটাকে further redefine kori. So you have your particle here that's moving in the field, and in circular motion, we know that the centripetal force is just a generic term provided to the force that's acting towards the center, but it's actually provided by something else, right? In this particular scenario, who provides my centripetal force? In this particular scenario, who provides the centripetal force? No. No. I'm asking you what's the name of this red arrow. What do you call this force? That's a little advanced, but you're right. So the correct answer is electromagnetic force. The electric field and the magnetic field and interact with a force. Magnetic force. The magnetic force is the force between what? A north pole and a south pole. Velocity is the force in that. Right. So my question was, who provides the centripetal force? And the centripetal force is provided by the electromagnetic force. So like last class the F that came out from the Fleming's left-hand rule, the motor effect is the electromagnetic force, right? It's the first time we generated force using what? Electricity and magnetism, right? Achha, anyways, so if my particle is going in a circle, I can say that the centripetal force is going to be what? mv squared divided by r. And what is my force, magnetic force, data? Electromagnetic force. This is the one I'm talking about, okay? Electromagnetic force. BQV sine theta, right? So BQV sine theta the dilemma because we are assuming it's perpendicular. Achha. So in this case, let's do simplification. V cancels out. So you get mv divided by r equals to BQ. And arguably one of the most useful equations in this chapter, R equals to mv divided by BQ. What does it tell you? It tells you that when a charged particle enters a field, the quantities that are responsible for the radius are these four: the mass, the speed, the flux, the charge. So, if your mass is a lot, the radius only bada hobe. If your velocity is a lot, the radius only bada hobe. If your flux strength is a lot, radius only chota hobe. There's a lot of force to spiral inwards, right? Charge bada hole, radius chota hobe. And this one equation can help you solve, like, I would say 80% of the questions you get from this topic. R equals to mv divided by b. Okay, m is mass, v is velocity, b is flux density, q is charge. And the good thing is sometimes they make you this is mass in kilogram. This is velocity. That is what to the field? All right, that is perpendicular. This is magnetic field strength or magnetic flux density. Magnetic flux density. And Q is the charge. Right. The thing I was saying that the good part is that they make you derive this. So any type of question you get, you'll find that you first have to derive this and then do your math. It's very similar to something we did in gravitational field, if you remember. T square equals to 4 pi square gm r cube. Barbar US supported the math. This is that version here. Barbar and then the last you derive and figure it out. Okay. And there was another thing that came sometime back, but আবার আসতে পারে ওটা হচ্ছে as the particle spirals, right? Spiral করতেছে. How does the time period change if the particle starts to spiral at different radii? Now এটা কখন হয় একটু explain করি. So there's something called a particle accelerator. I don't know if you know this. Yeah, CERN, Large Hadron Collider, LINAC, cyclotron. These are devices where we take particles to very high speed, right? And we make them spiral. And they keep going fast and fast and fast, and we make them collide with something, and it produces the shower of particles. We discovered the quarks, the leptons, and everything else, right? Unfortunately, on the syllabus at night, but it's like one of the core chapters out there. No, it's actually an interesting topic. So, thing is, what they did 2022, they sneaked it in on the syllabus in the most unassuming part of your syllabus. There's a chapter called medical physics. There's something called a positron emission tomography, a PET scan. With PET scan, you need this chemical called fluorine 19. With chemical to create you need a particle accelerator. They just put it there, and then just one paragraph on the entire working of a particle accelerator, just so that you can get fluorine 19 that can be used in the diagnosis of cancer. So it's now in your syllabus, but this was the place where it should have been. Not there. So eventually you learn a small amount of it, but Jeta use for it, the hospital use for it. They're like small portable versions of it. Okay, not really portable, but you can put it in a hospital for home size. Small particle collectors. Very expensive. So yeah, but I don't think they can operate it. That's what I've heard. Yes, at least we can say aste. The point was not just Cholrenaki. The point is aste, just like our satellite. Right. So what happens to the time period here of your oscillation? So time period, what you're going to do is we'll do the same thing in circular motion. Fc equals to Fb, but this time we'll go for another equation of circular motion that has time in it. Do you know another centripetal force formula that has time factor in it? Yeah, m omega square r. So m bqv and m omega square r equals to bq. Do you remember what v is in terms of omega? V equals to omega r. So omega cancels out. So m omega r equals to bq. Omega is what? 2 pi by t. So m 2 pi by t r equals to bq. Now I'll show you key bqr. So do you see that there's an r on the left and the right? What will they do? Cancel out, and we find something interesting going on here. The time period that a particle takes to undergo circular motion in a magnetic field is actually independent of radius. মানে তোমার radius যত বড় হয় যত ছোট হয়, the time it takes to spin and make a circle is always the same. Okay, so this is that equation out there. So exam যেটা আসলে frequency বলছিল, so frequency কি হবে? bq divided by 2 pi n. Basically ulta kore dewa. This is 1 by time period, right? So yeah, this is another relationship that showed up in this topic. Other anticipation kintu je tomra exam er boshe eglaki derive korba. Acha, so just keep that in mind. Eta kintu oi point of view theke dicchi je it's something that you should be able to do it once you understand the chapter. Right, so questions thakle bolo. I'll show you some demonstrations, but are you clear about the idea behind this topic? So we now understand that when charged particles enter a magnetic field, they experience a force, and the force is going to be perpendicular to the magnetic field, and the force is always acting towards the center. As a consequence, what does your particle do? Spirals in a circle, right? So therefore, circular motion is sub equations below active. You can use all of them, right? Now, some complex scenarios would be that the particle enters at an angle because of which it's going downwards and also spiraling, so it forms like a helix, right? Also, what if your particle is losing energy? What will it do? Will it spiral at the same way, or will it get a bigger circle, or will it spiral inwards if it's losing energy? Yep, R equals to mv divided by bq. So what happens to your velocity? Decreases, so the radius decreases, okay? So J, all levels of beta particle does spiral inwards also. And the reason was that the beta particle was losing what as it went through the chamber? Energy, okay? So yeah, these are more or less what we have seen so far. এটা কেমনে হয়েছে? So imagine তুমি এই diagram থেকে top view থেকে দেখো. Let's just look at it from the top. So if I look at it from the top, you have this magnetic field here, and you have your particle that's entering like that, and this is the velocity. Okay, let's call it v cos theta. So what is this velocity to the magnetic field? Perpendicular. Can you tell me which way is force acting? If it's negative charge. তোমরা বাকিটাও ট্রাই করতে পারো। Can you tell me negative charge হলে কোন দিকে force act করতেছে on this particle? What opposite? মানে what's the actual যেটার opposite? Downwards. বলো, আমি ভিতরে magnetic flux তো ভিতরে। The x is into the page, and this is the velocity, right? So find the direction of force. Downwards. Right, FBI, current is this way, right? Magnetic flux is into the page, which is my thumb pointed upwards, right? The lancing upwards. No, answer is downwards, because this is a what charge? Negative. So whenever it's a negative charge, what's the direction going to be? Reverse, right? Okay, anyways, now that's out of the way. What does the particle do to it? It goes down and makes a circle. So yeah, this is the top view of it. So when you top view থেকে দেখো দেখো যে particle টা just এরকম circle করতেছে. But is that the only velocity it has? No, right? So তুমি যেটা দেখতেছো is you're seeing the top part of this diagram. But isn't there a part that goes down as well? That velocity carries it downwards while it's doing the circle. So as a result, কি হচ্ছে এটা নিচের দিকে চলে যাচ্ছে and also circle করতেছে, becomes like a helix, right? If this component is very small, the spiral would be very tight. And if the component is very big, you'll find that it's very loose, like a staircase. Okay, let's see some demonstrations of this. Question থাকলে আমাকে বলো। Okay, so we will fire a particle and see কি হয়। So you give a particle there and it's going like that. Now, eta is actually 3 dimension. So I mean, this is the helix that I was talking about. Do you see how it's climbing up? So there's a component of this that is what? Vertically upwards, and there's a component of this which is what? Towards the center. So it's going in circles because of that component towards the center, and that vertical velocity is taking it upwards, right? Our top থেকে দেখলে is just doing circles like that, right? So gravity is very negligible on these particles because g is very small, mass is very small. So this is the version that we'll be working with. So your magnetic field is given here, a dot. What does dot mean? Out of the page. So let's show, like, put a particle inwards. So it spirals like that, right? Now I want you to tell me what can I do here so that the particle spirals upwards and forms a tighter circle. So আমাকে এই parameters গুলো change করতে বলো যে কি change করব. So the particle spirals upwards, number 1, and it's going to be a tighter circle. Decrease velocity, decrease the charge. Decrease the charge, নাকি increase the charge? Decrease. Do you all agree? Charge decrease. R equals to BQ, MV divided by BQ. So to have a tighter radius, more charge or less charge? R equals to MV by BQ. More charge, right? More charge. Mass ki beshi na কম? Calm, right? Right. But I want it to go upwards. How can I do that? So change the charge to negative, or I can make my magnetic field which way? The other way, right? So that option is also there, by the way. So কোনটা করব? Yeah, because if I do both of them, they come back to the same, right? So charge negative করে দিলাম. Let's try কি হয় দেখি. Yes, that's what happens. Okay, so it was there. পুরো circle হবে না কেন? Why can't I make it go full circle? Because as it does like a half circle, it's back out of the field again. So full circle, you need to have the force acting towards the center when? Always. That scope is not there. But a কখন possible হতো if the charge particle started where? In the center of the field, and somehow it started moving, right? So তখন এটা হবে. But তোমরা কি basic idea টা বুঝছো behind this thing? So yeah, this is it. Velocity vector say it too. So it's slightly at an angle. Okay. আর একটা দেখাইতো অনেকে. Confusion থাকলে আমাকে বলো, okay? আচ্ছা আমি ওটা দেখছি একটু পরে, but আগে just note down basic definitions from this. So yeah, in the exam, if they ask you, which they do very often, why does a charged particle undergo circular motion in a field, right? Anyone wants to volunteer the full answer, 4 marks? Why does a charged particle undergo circular motion in a magnetic field? Yeah. Okay, let's start with 3 marks. I mean, 3 marks probably 4 marks to come. You started very well. Suddenly you're like, that's what goes in circle. I mean, it's a good start. That's like a 1 mark answer. আচ্ছা আমি বলি তোমাদের এইটা অ্যানসার করার প্রবলেমটা কি হয়? You guys start with the reverse argument. The proper argument would be a charged particle in a magnetic field, right, goes in a circle and undergoes continuous change in direction. A continuous change in direction results in a change in velocity. A change in velocity leads to a what? An acceleration. And to provide the acceleration, a force is required towards the center of the motion, which is provided by the interaction of the magnetic field and the movement of the charge, and hence it maintains the circular motion. Yes, all circular motion answers because they're all the same thing eventually. It's just what's that other force towards the center. And the ulta bolo, it is difficult. I understand. You'll say that the object is entering, there's a force towards the center, but then why does it go in a circle? Like if there's a force towards the center and the motion is this way, right, perpendicular, why does it go in a circle? Yeah, so এখানে যেটা হবে that there is no change in magnitude, but there's a change in direction, and because the force is acting towards the center, there's a what change in direction? A continuous change in direction. As a result, the object continues to move in a circular path. I'm not a fan of this answer. Koneta marks power difficult. If you go the other way, there's a lot of there's a proper sequence to it. Change in direction, change in velocity, acceleration, force. This is the force, right? I think that's the better way. So you can have given both of them, but alternate to the some students want to do it, but I think the first one is the more natural way of answering. Okay. Next week. আচ্ছা তোমাদের হচ্ছে Tuesday সকালে ক্লাস নেওয়ার কথা ছিল বলছিলাম, right? সকালে। Yes, I talked about it. না তোমরা তো বলছো Sunday, Tuesday কোনো problem নাই। we discussed this. It was supposed to be tomorrow, but I said I'll let you know, so I'll take it on Tuesday. So কি করবো এই ক্লাসে? I'll solve a question paper. কারণ তোমাদের school exams and most of the syllabus is going to be the magnetism or something. It's only for school exam. All মানে question paper যতগুলো আছে সব টপিক থেকে একটা question. So I found a paper যেখানে I think তোমাদের হচ্ছে alternating currents আছে exam এ। আচ্ছা, so like half wave rectification, full wave rectification. Okay. Third, maybe I can do 1 or 2 more questions before that. Till AC current, I'll be done with the parts of magnetism. AC current হচ্ছে maybe now. So this one you finished. But AC current is like the smallest topic. Because I remember তোমরা বলছো এটা করছিলে in a week. Past month, so anyways, Lenz's law ogla baki আছে ogla আমি করব, but yes, on Monday you have your normal class, by the way. Tuesday morning I will have like a class for paper solving. Okay, 10:30, 11. It's just going to be online. সকালে এমনি করতে যায় না। No, for me, but you're not allowed.